Okay, now let's talk about what are K-regular graphs and what are complete graphs. Now, a K-regular graph is basically a graph which has the same degree. So for example, if I say one, I have one regular graph, that would just be two dots connecting, two vertices connected with one edge. Basically, this K is denoting the degree that you have in that graph, the degree of each vertex. So the degree of this vertex is also 1 and this is also 1. So for two regular graph, that would be, oops, draw this, a box. So for two regular graph, the degree of each vertex in this one is 2. That's the reason why we call it two regular graph. Similarly, we can have another version of true regular graph as a triangle. So the vertex of each of this graph will also have a degree of 2. So there can be multiple representations of two regular graphs, and similarly for multiple representations of three regular graphs as well. So the graphs are not unique in K-regular graph. An example of a three regular graph would be just a box which is basically connected to all of the other vertices, and for this one the degree for each vertex would be 3, 3, and 3. So that's K-regular graphs. And the total number of edges of at any point at any graph would be defined as nk divided by 2, where k is the degree, n is the total number of vertices that I have divided by 2. So let's say take this one, these two. Let's take this one and this one. So the number of edges in this one is 1, 2, 3, 4. And if we want to prove it by this formula, then the number of vertices are 4 times the k value over here is 2 divided by 2, and that indeed gives you 4. For this one, it would be the total number of vertices are 3 times the regular graph, the degree of regular graph is 2 divided by 2, and that gives you 3. So this checks out. So that is the formula for the total number of edges. We will be looking at how to basically prove this formula for the number of edges and the edges of complete graphs in the future videos of proof by contradiction, induction, and direct proofs, and etc. So we will be taking a deeper dive over there. Then we have a complete graph. And a complete graph is basically just a simple graph. And if you remember what a simple graph is, a simple graph is basically having no multiple edges and no loops. So, which basically means that complete graph is a type of a simple graph where every vertex is connected with each other. Which means if I have, let's say, the way how you denote complete graphs is by k of 1, k of 2, k of 3, k of 4. Let's take k of 2. So a k of 2 would look something like this. Now notice over here, I am talking about every vertex being connected to each other, which means I made a small mistake. The graph of k of 2 is going to be just a simple line, because the complete graphs basically means the number of vertices. This n basically denotes how many vertices that you're gonna have. So in this one, that's just gonna be a dot. In this one, it's going to be 2 vertices which should be connected to each other. For 3, that's going to be 3 vertices connected to each other. For 4, this is going to be a box, right? 4 vertices which are connected to each other. So this one is connected to this, and then we're going to do the same thing over here, this, and that completes it. So that's a complete graph. The degree of any complete graph is given by n minus 1. So as you can see over here, 1 minus 1 would be 0. So the degree of this vertex is 0. For this one, it's going to be 2 minus 1. So the degree of each vertex is going to be 1. And for this one, since you have 4 vertices, so 4 minus 1 would give you a degree of 3. So this checks out. Then we have the total number of edges, and the total number of edges is given by n minus 1 divided by 2. Again, this, like I said, this formula will also be proven in the later videos by the proof of contradiction, induction, and direct proofs, etc. So the total number of edges in, let's say this one, which we figured out was 3, we're going to prove that using this formula. So this is going to be n minus 1 divided by 2. N is 3, so 3 times 3 minus 1, which is 2, and this cancels out, and we're left with 3. So the number of edges is also working out. Now, another very important observation that we can make in the complete graph is that a complete graph is just a version of a simple graph which has the most number of edges, which means that, let's say if I had a box, right? I had a box. This graph. This can be classified as a simple graph. But if I connect them to each other, now this is the most complete version of the simple graph which will have the most number of edges for each vertex. Now there's no other graph in which in any way how I could modify this, having 4 vertices with having more number of edges for this graph. So that is what this point basically means. Okay. Now let's take a look at what is the clique size. Now the clique size is the largest n such that Kn is the complete subgraphs that can be spotted. So basically, what I'm trying to say over here is that it is going to be a complete graph. It is going to be a complete subgraph. What are subgraphs? Subgraphs has been covered in another video, so you can check out that video, and from there you can understand what a subgraph is. Subgraphs will not be covered in this tutorial or in this video, but basically what it means is that we are going to be creating a complete graph, and we just discussed a complete graph is basically a graph in which every single vertex is connected to every single vertex, every single other vertex. So for example, let's take T over here. So T is connected to U. Is this a complete graph? Yes, it is. It is a complete graph. However, there's a restriction that we have, and the restriction is we need to find the largest n, which means we have to find the largest sub-complete graph in this whole graph. So if we pay a little bit attention, T is connected to U, and T is also connected to V, and U is also connected to V. So this is another subgraph. So we have found K3. Is there a possibility that we could find K4 in here over here? Let's see. T is connected to W, and W is connected to V, but W isn't connected to U, so that's not a possibility. Let's try X. T is connected to X, X is connected to U, and X is connected to V. This is a complete graph. So we can say that there is indeed K4, and K4 is basically defined for the vertices T, U, V, and X. So the largest clique size of this graph is going to be K4. Okay, moving on. What are graph complements? So here I have two graphs, and before I continue with graph complements, let me just revise a little bit. So we talked about what are K-regular graphs and what are complete graphs and what is the clique size. So K-regular, basically K is representing the number of degree. So one regular graph would mean there's 1 degree, two regular graph would mean there's 2 degrees, three regular graph means 3 degree of each vertex. For a complete graph, we're talking about a simple graph where every vertex is connected, and we're talking about the number of vertices. So K1, 1 is denoting one vertex, 2 is denoting two vertices, 3 is denoting three vertices, and 4 is denoting four vertices, where every vertex should be connected to each other. Then we have a clique size, and clique size is basically the complete subgraph, the maximum complete subgraph that you can find in a graph. So in this case, that was K4. Okay, now let's take a look at what are graph complements. Now graph complement is basically, I have, this is, let's say we have to find out the complement of this graph. And this is just a complete version that I've drawn for this graph, where every vertex is connected to each other. Now, graph complement basically means is that for every edge which is not connected to each other, that would be the resulting complement. For example, we can see that the green lines, the green edges in this graph are not connected, or they're not visible in this graph, which means the complement of this graph is actually the missing number of edges, so which would be this thing. Whoops. This is the complement of this graph. So this is the complement of this graph. Another example could be, let's say, this one. So the complement of this would just be this.